Assalamualaikum and good evening. My name is Nur Shafinia Zati and my metric number is 187948. I am from University Putra Malaysia, Faculty of Engineering, Department of Computer and Communication System Engineering. Today I would like to present my project named Supercontinuum Light Generation via Random Distributed Feedback Lasing. My supervisor for this project is Dr. Nadia Husseini binti Zainal Abidin. So, today's presentation containing introduction, methodology, result, and also conclusion for this project. Firstly, I will present the project background. Supercontinuum. What is supercontinuum? Supercontinuum is also defined as broad as a lamp which is flat and broad optical spectrum, and also as bright as a laser. How does it form? It forms when a collection of non-linear processes act together upon a pump beam in order to cause severe spectral broadening of the original pump beam. Why it is chosen for this project? Because it have features that is high output power, a broad flat spectrum, and a high degree of spatial coherence that are highly desirable for many applications. For example, optical coherence tomography, spectroscopy, optical frequency metrology, optical component characterization, and many more. Next, random fiber laser. What is a random fiber laser? Random fiber laser is a fiber laser that does not utilize the conventional resonant cavity to induce lasing. It also does not use physical mirrors for feedback in gain medium. How does it work? The backscattering of light, which is Rayleigh scattering, is an excited gain medium, creates randomly distributed mirrors along cavity for light feedback. Why it is chosen? Because it has clear advantages for supercontinuum generation, including simple technology, low cost due to the dispensable need for specialty fiber, and also low coherence. Next is problem statement. The problem statement for this project is the complexity and higher cost of configuration for supercontinuum generation in conventional resonant cavity. The design of such scheme has been rather complicated and costly due to the use of specialty fiber and multiple components to optimize generation. And the second problem statement is the strict requirement for effective spectral broadening. The pump source wavelength needs to be within anomalous dispersion region for conventional resonant cavity. The aim for this project is to develop and investigate supercontinuum light generation via random distributed feedback lasing through manipulation of cavity length and design. And the objective of this project is to investigate optimum length of true wave fiber for supercontinuum generation. And the second objective is to enhance supercontinuum generation through integration of highly nonlinear fiber length in cavity. And the third objective is to analyze performance of supercontinuum generation with position variation of highly nonlinear fiber in cavity. And lastly is to generate a broad optical spectrum that extends beyond C-band, which is from 1530 nanometer until 1565 nanometer using RFL. Next, the project scope. Project scope is firstly to study the study focus into the design and development of the fiber laser. The fiber laser is in this study is mirrorless, whereby the gingium is unbounded by reflectors but achieve feedback through Rayleigh scattering. This type of laser is also known as random fiber laser, where the term is coined based on the randomness of the feedback. Then, supercontinuum generation via random fiber laser is proposed in this study based on the combination of single mode fiber and highly nonlinear fiber. Next is methodology. This is the project flowchart. Firstly, component characterization, which all the component will be characterized first, and then splicing of experimental setup using splicer, and the next step is variation of true wave fiber to determine optimum length, and lastly the enhancements of supercontinuum generation through high nonlinear fiber integration and position. Okay, this is the result for component characterization. Characterization of the Raman pump need to be done before running the experiment. The Raman pump is splicing with the SMF pigtail, then connected to the optical power meter, which is OPM, to read the output power. Value of Raman pump is inserted using online software named Kyopsys. Okay. This is the graph of OPM in watt versus Raman pump in milliampere of the characterization of Raman pump. Value of Raman pump is tested from 1000 milliampere to 7800 milliampere with the increment of 50 milliamp each. From the graph above, it is shown that the Raman pump is good condition since the output power keeps increment together with the value of Raman pump current diode. And next is experimental setup. This is the experimental setup for this project, which each component is connected by using splicing technique, and the splice loss should not be more than 0.03 dB for each splice to avoid too much loss in this experiment. The 1% connector will be connected to the OSA to prevent high power damage, while for 99% is connected to the OPM to measure input power. Isolator is used to allow light in one direction and prevent Fresnel reflection. And it also helps to ensure the feedback is only from Rayleigh scattering. The first wavelength division multiplexing, which is WDM, that Raman pump injected is for monitor output power backward and forward multiplex pump signal into cavity, while the second WDM is for observing depletion of pump. Lastly, true wave fiber is used since it high Raman gain since it have a high Raman gain coefficient. Next, this is the advantages of true wave fiber, which is the first one is high Raman gain coefficient, so that it can have some amount like in the gain medium, and it also has low and stable full spectrum performance to maximize transmission distance and minimize transmission power. And lastly is less expensive than other fiber. Generation. This is the generation. The next one is generation through highly nonlinear fiber length variation. Highly nonlinear fiber used to get broader spectral bandwidth, and it has high coefficient of nonlinearity, which means this type of fiber has small effective of fiber. And the benefits for this type of fiber is easy splicing and simple technology, very precise dispersion control, and low loss will happen during the experiment. This is the second setup, which is the highly nonlinear fiber is placed in position A. This position of HNLF, which is highly nonlinear fiber, is conducted in order to observe either position A or position B will give the best spectral broadening results. And this is the second setup, which is the fiber is placed at the position B, and then we will see the results. This is the true wave length result. Based on the graph, 36 km of TW fiber is chosen as the optimum length for the generation of supercontinuum light because it demonstrates better nonlinear spectral broadening than 72 km. And this is the next result, highly nonlinear fiber position result. In line with observations for position A, the spectrum managed to broaden until 56 nanometer, which is 5.25 watt. With increasing pump power, the dominant peak changed from 1555 nanometer to 1565 nanometer. While for position B, the line width shows good broadening until 180 nanometer, which is 5 watt. Starting at 4.48 watt, the 1554 nanometer peak is suppressed while the 1565 nanometer peak grows. And lastly is conclusion. The conclusion for this project can be made shows that 36 km of true wave fiber is chosen as the optimum length for supercontinuum generation due to better nonlinear spectral broadening. Position B of 300 meter highly nonlinear fiber show best performance for supercontinuum generation with 180 nanometer 20 dB bandwidth. And lastly is supercontinuum generation via random distributed feedback is successfully achieved with performance comparable to conventional laser. So that's it. Thank you.